We'll wait just 2 minutes and I'll start in case anybody wants to join in.
The connection went off, so I solved them and sent them later.
What I said was, since you had an exam, I'm not going to correct this assignment for you because if you remember, we're going to be correcting 2-3 assignments randomly throughout the semester.
Yeah.
So usually I won't do that, but just for you, and since you had an exam, I won't correct it for you. So
Okay, thank you.
next week work harder on the assignment, and just like Professor Said says, we care more about you understanding the material, learning the material, not so much about, don't worry about the grades, just worry about learning.
Okay, thank you.
Welcome. Yeah. We'll start in 1 minute. Okay, hello everyone, and welcome to the second practice exercises set. Just like the recitation, I'm gonna have this meeting weekly, and I'm gonna have the meeting open by 4:55 p.m. at the latest. So try to join in as soon as possible so we don't waste time. Because we really only have an hour to go through as many exercises as we can. And this assignment is pretty long, so I'm gonna go over every exercise, but I might not go over all the parts. I'm gonna choose the parts that I found most important. If I go through an exercise and I didn't go through a part that you didn't understand, stop me and let me know and I'll go through it. Okay? So if there's a part that I don't go through and you don't understand, stop me and I'll go back to it. So exercise 1 was pretty easy. I just care about part B. So there, in part B, we have for every P of X implies for every A of X. So if all Lebanese citizens are politicians, then all Lebanese citizens are above 25 years old. This is different than saying for every X, then you open brackets, P of X implies A of X. And even without the brackets. The one I just wrote, this means, hey, for all people, for all the citizens, if you are a politician, then that means you are above 25 years old. But part B isn't saying what I just said. Part B is saying, if everybody is a politician, then everybody is above 25 years old. If everybody is a politician, then everybody is above 25 years old. So they're different. And I think we solved this in the recitation where we were asking either this or something similar if they're equivalent. Like, can I just distribute the for every x? And it was false. So it's not necessarily that these two are equivalent. Okay, that's all I want from exercise 1. Moving on. Exercise 2, we also went through in the recitation actually. So in exercise 2, we only have 3 parts, but in the recitation, I think we saw there was like maybe 6 or 7 parts. So just a predicate that takes 2 inputs. Now, I care again about part B. So there exists y for every x, t of xy. So we want the original negation and then the English negation. So the translation is, there is a CMPS course that has been taught by all CMPS professors. Okay, so there is one course that was taught by everybody, and it's the same course. The same course has been taught by everyone. This is different than saying, for every x, there exists y. For every x, there exists y, t of xy. This is different. Why? Again, let's go through the first one. We're saying there's a course, let's say CMPS 211. That's your y. And we're saying that this course was taught by all CMPS professors. So professor 1, 2, 3, it was taught by all of them. The same course was taught by everyone. What I wrote here is saying all the professors have taught a CMPS course. So for example, P1 taught 211. Professor 2 taught 209. Hey, Professor 3 might have also taught 209, or maybe even or maybe he taught both 209 and 211, who knows. The difference between part B is part B, we're saying, hey, we specify what the course is, and then we move on to the professors. Here, no, we specify the professor, then we say, hey, what course does this guy teach? Okay, so that's the difference. I'm going to give another small example. Let's say I have for every x, for every y, there exists z. Imagine like there's a timeline. So first off, we have to start with every x. And since we have for every x, we have to do that for all of them. So for every x, x1, x2, x3, and so on. Then for each x, you have to say for every y. So for this x, y1, y2, so on. For this x, y1, y2, so on and so on. Then we reach that there exists z. So for every y here, it could be a different z. Here it could be z1. Here it could be also z1. Here it could be z500. Okay, this is what I just wrote. Other way, let's say it started with there exists z, and then we said for every x, for every y. Hey, you start, hey, you only have one z, so it has to be one of the z's. And then you say for every x, so x1, x2, x3, and you get the idea. Then you split for the y's, and so on. So in the first one, x, then y, then z's, so it could have been different z's for all of them, whereas in the other case, it was just one z. Okay? I hope you won't have any trouble with this. Any question before we move to part 3 on either exercise 1 or exercise 2 before I start here? Okay, good. So we have some stuff, predicates. Okay, no questions, good. So T of PL is Turing complete, PL. Now, this isn't a constant. It's not like a specific thing. This, you can see it like X, okay? So yeah, variables or whatever your input, it could be made up of more than one letter. That's fine, as we'll see with predicates also later. Where the domain of PL is all programming languages. So that's why they gave it PL. It's kind of a shortcut, programming languages. Express each of the following, blah, 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 blah. Okay, so each one of these statements from A to F, we have to translate them. And then, it's okay, Hussein. We're in exercise 3 now. So from A to F, we have to translate them into logical connectives, predicates, all that cool stuff. And then we're going to be given A to F as premise, like A to F are going to be true. And we want to see if we can conclude F or not. Like if A to E are enough to conclude F, or do we need something extra? So first, let's see some translations. Okay, so some programming languages are not Turing complete. So there exists some programming language such that it's not Turing complete. All compiled programming languages are platform independent. All compiled. So for every programming language, if it's compiled, then that means it's platform independent. Whatever those statements mean, we're just translating. Okay. Now, for some reason, we have the original negation and English negation. You don't have to do that. This might be a mistake coming down from here. Okay, what we care about is the original. Any language that is Turing complete is either interpreted or compiled. So this is your XOR. It's an exclusive, either this or this. So for every programming language, if it's Turing complete, then you have the XOR between these two things. And so on. Okay, all the other stuff. Now, the question is, A to E. Are these enough to get F? F just says, I'm going to have some programming language, and this language is going to be Turing complete, and it's, what's B? And it's platform independent. So do I have this? And the answer is no, I don't have it. Why? Simply you can't reach this. Now in the solution, they're going to tell you we can have that Java is platform dependent. Where do we have this? From here. Yeah, we have C of Java. And
Put 2 points beside the.
what did you say?
When do we put the 2 points beside the exist or beside the predicates?
If you don't put it, it's fine. This is just it's kind of like saying that
Separating?
the PL is for everything. Okay,
Okay,
so
thank you.
you don't need to put it. It's fine. Okay. Or like 2 points you read usually you could read it like such that. So like here we're saying there exists a programming language to a column, so such that it's both Turing complete and platform dependent. So
Okay.
we can conclude that Java is platform independent because from E we know that it's C of Java, and from B, C of Java implies B of Java. This is modus ponens or something like that. I forgot what the name of the rule. But you can't find that it's Turing complete. So going to the solution, we can deduce the conclusion. We know that Java is independent because what have I just said? But no premise can tell us that Java is Turing complete. So F can't be concluded. One of the solutions, you can do this. You can add a premise that says T of Java is Turing complete. And then you're done. Because like we said, we do have P of Java. So if you add a premise that says T of Java, then you're done. That Java is Turing complete. Makes sense, right? So if we go by that, this is where they got P of Java. So we have these three things. Simplification, we get C of Java, and 1 and 3, yes, it's modus ponens. So 1 and 3, we're going to give you P of Java. And then simply, you added this new premise, T of Java, so just add them together. Okay. If you found a different way to reach the conclusion, then that's fine. Like if you added another different rule. Okay. If you have any problem on exercise 3, let me know now. So again, the answer was no, we can't reach the conclusion. We had to add T of Java. Which part in number 3 you didn't understand? C and D. Oh, so like the translation? Okay, sure. Okay. So any language, part C first, any language that is Turing complete is either interpreted or compiled. So interpreted and compiled are one of those properties that you will either have one or the other, but not both. So it's an exclusive or. Okay, it's exclusive. Your language is either interpreted or it's compiled. It can't be both at the same time. So these two things, you have XOR between them. And the statement is saying any language that is Turing complete is going to be either this or this. So the translation becomes, for every language, if it is a Turing complete, then you get the XOR between them. Okay? That's part C. Part D, same idea. A programming language is either compiled or interpreted, but not both. So you put the XOR again. It can be, welcome, you're welcome. But for part D, like they specified, but not both. So it was kind of easy to see the XOR. In part C, since they didn't put but not both, it might have not been clear for some of you. So if for some reason you put a normal exclusive or a normal inclusive or here, then I won't say it's wrong because it should have been added but not both for part C2. Okay. Good. Exercise 4. Translate in two ways each of these statements. First, the domain is going to be students, and then the domain is going to be all people. We solved something like this in the recitation, where the domain changes. And you can define predicates whenever necessary. Again, this is something that we did. We just add predicates, so we're able to actually translate the sentences. And I guess maybe here we're going to see that the predicates don't have to be just one letter. So let's just jump into the solution. So the first one, where are you? All students who can code in Java can code in JavaScript. So we made a predicate codes in. Okay, codes in, and it takes two parameters, P and L. Person P can code in language L. So first, if our domain is student, okay, so if our domain is students, then when you say like for every X, you know that X is a student. Or you could say for every ST, like short for student. For every ST, codes in ST Java. So if a student codes in Java, that means that this student also codes in JavaScript. Done. Now, if your domain is people, you have to specify that this person is a student. So we start for every P, for every person, student of P, S of P. So this person is a student and he codes in Java, he or she, then this person, the student, also codes in JavaScript. So same thing as above, the only difference is at the start, you have to specify that this person is a student. Okay, simple enough. Now it gets a little...
But doctor,
Yeah.
why حطينا السيمبل تاع الاند مش implies مثلا.
Uh,
يعني as في implies codes and لانه هو يعني is coding in Java.
so you're saying why didn't we write this codes
Uh,
in B Java, and you want also another implication implies codes.
yes.
Okay. So what we just wrote, we're saying if a person is a student, then this person codes in Java. Okay?
Okay.
If this person is a student, then he codes in Java. But the statement is saying no. A student, all students who code in Java, then they code in JavaScript. Okay?
Mm,
What
okay.
we wrote here assumes that every student will be able to code in Java. But no, it's the ones that do code in Java can code in JavaScript. Deal?
Okay.
Okay,
Clear.
great. Part B. Now this gets very interesting. Some students can code in exactly one programming language. This is one of the keywords, exactly one. So you have to specify this somehow. Let's see how. Again, first domain is just the students. So there exists a student, and there exists a language L1. This student codes in L1, and for every other language, if L1 is different than L2, then this student does not code in L2. I'm going to read that again, and I hope that you're starting to be able to read these sentences just like I'm reading them. Like I don't see any difficult, weird, mathy symbols. It's just a language. You're reading French, you're reading Arabic, you're reading English. It's just a language. So one more time. There exists a student and there exists a language L1. Such that, so again, these two dots, such that this student codes in language L1. And for every other language L2, such that L1 is different than L2, then this student does not code in this second language. Okay, because he has to code in exactly one language. So to solve this part, step 1, say that he codes in a language. Step 2, say for every other language, if it's not the first language, then he doesn't code in it. Okay? The second domain is the same thing, but you're saying there exists a person, and this person is a student. You just have to add this part, and the rest is the same. Any problem? If you have a problem with part B, let me know now, because part C depends on it, kind of. Or it's like an expansion of it. So some students, again, when we say some students, we're going to be using there exist, can code in exactly two programming languages. Exactly two programming languages. So there exists a student, there exists language 1 and language 2, such that this student codes in language 1 and he or she codes in language 2. And for every other language, so L3, for every other language, if he codes in this language, then L3 equals L1 or L3 equals L2. Again, we break it down into two parts. Part 1, you say that this student codes in language 1 and language 2. Then you say for every other language, if he or she codes in it, if this student codes in it, then this language has to either be L1 or be L2. Okay, like it can't be some new language L3. So L3 is actually either L1 or L2. Now, the only thing that I feel might be missing is we have to specify, like you could add here, and L1 is different from L2. I think this might be missing, because if you don't specify that L1 is different from L2, they could be the same. And then you're no longer saying exactly two programming languages. So yeah, I think just this part is missing. Clear? Same for all people. So far, the second domain isn't different. You just have to specify that this person is a student. And again, L1 different from L2. And you didn't understand the L3 part. Okay. So some students can code in exactly 2 programming languages. So you have to translate this in a way where the student exactly 2 programming languages. So it's as if I'm talking to you. I'm telling you, I code in Java and I code in C++. And if there is some third language, L3, that I code in, then L3 is either going to be Java or it's going to be C++. So this is what I'm telling you. I code in exactly 2 languages, which are Java and C++. And if there's some third language that I do code in, then this third language is either Java or C++. Okay? Because I code in exactly 2. In part B, what we said was, if there was another language different than L1, then I don't code in it. You could have done something like this, but this is like a different way. We're saying, hey, if there's a new language that I code in, it has to be either L1 or L2. You're welcome. Okay. Take a look at D and E. I'm going to skim them right away, and I'm going to see if there's anything difficult in them. Either way, otherwise we'll move on. Okay, part D was easy enough. Nadia doesn't code in any programming language that Nadim codes in. So simply we say, for every language, if Nadim codes in this language, that implies that Nadia doesn't code in it. In the second point, you just have to specify that they're both students. Easy enough. Let's read part E together. Marwan can code in some, but not all programming languages that Manal can code in. So Marwan codes in some, but not all the programming languages that Manal codes in. So there exists a language Marwan and Manal codes in, and there exists a language that Marwan doesn't code in, but Manal does. Okay. Makes sense. It shouldn't be an implication because we didn't say that Marwan couldn't code in something that Manal doesn't code in. Like, my first impression, I thought, hey, maybe we can say if Manal codes in something, then that means Nadim codes. Because they told us Marwan can code in some, but not all the programming languages that Manal codes in. So it makes sense to say, hey, if Manal codes in something, then, oh, actually, I think it should be in reverse. So it makes sense to say if Nadim can code in something, then Manal definitely can as well. But that's not what the statement is saying. The statement is saying simply, Marwan can code in some of the languages that Manal does, but not all of them. So Manal, let's say Manal codes in Java and C++, and Nadim codes in Java and Python. So in this example, E holds true, right? Manal codes in Java, C++. So Nadim codes in Java, so he codes in some of the languages that Manal does, but not all of them because he doesn't code in C++. But at the same time, it's true for Manal. So Manal also codes in some of the languages that Nadim does, but not all of them. She doesn't code in Python. So that's why the implication doesn't work here. We're not saying that every language that Nadim codes in, Manal is going to code in them, or vice versa. Okay, clear? Okay, good. That was interesting. Let's see exercise 5. I think we're halfway through the hour and we're halfway through the exercises. So hopefully this is a good pace. Okay, I'm gonna start with exercise 5 again. If you have any problem with the previous exercises, let me know now. Okay. Express these propositions using quantifiers. Make sure to specify the domain of each variable you use and the predicates. So we want to translate from English to what we've been seeing, but we have to specify all the domains for each variable and what predicate functions we use. So for example, when we see here all CMPS students know all CMPS instructors, right away you at least know you're going to have a student domain and you're going to have an instructor domain. And you probably might have a domain that makes both of them common, which is like a person. Enough speculation, let's actually see the solution. So all CMPS students know all CMPS instructors. So P is all people, S is all students, I is all instructors. So we have 3 domains. We also have 3 predicates. S of S is a CMPS student, I of I is a CMPS instructor, and K of P1, P2. P1 knows P2. This is why we needed a third domain, because of the K, P1, P2. You may have been able to get away with it if you would have said K of SI, such that like where student S knows instructor I. You may have been able to get away with it if you did that, but I think it's cleaner to split everything up. So what's the translation? For every student, for every instructor. Actually, these are just variables. So for every S, for every I, here we specify that S is a student, and here we specify that I is an instructor. Then K of SI. Because remember, all students know all instructors. So for every S, for every I, for every possible combination, S knows I. Okay? So again, if we want to draw the thing that we would draw, S1, S2, S3, and you keep going till you reach Sn, like the nth student. Like if n is 1,000, if we have 1,000 students, then, so this is for every S. Then in each S, you have to say for every I, for every instructor. So I1, I2, I3, up to IM. Let's say M is 100. We have 1,000 students and 100 students. 1,000 students and 100 instructors. For all of these, you have K of S1 and I1. Here I have K of S1, I2. So in the first block, we're saying student 1 knows all the instructors. And then here, for student 2, you say he also knows all instructors, and da-da-da-da-da, all students know all instructors. Okay. Part B is fine. Okay. So I'm gonna jump to part F because they say bonus. So I assume part F is like hard or something. So if you have problems from B to E, let me know. But before that, let me first do F. So all students except one single student, so this is like saying except exactly one student, have visited at least one room in all buildings at AUB. Let's see our domains. B is all buildings. R is all rooms, respectable, of course, at AUB in both of them. We have a predicate function. So in RB, R is in B, VSR, S visited R. The reason we don't have a predicate that's or a domain for students or a predicate because it's already, I think, given. Oh, it wasn't already given. We'll see what happens. So this is basically equivalent to saying exactly one student didn't visit at least one of the rooms, at least one room in all buildings. So they didn't visit any room in some building. Ta-da. Here it is. Take a look at it for a minute. When you look at it, try to read it like I do. And we have to break it down like before into two parts. So again, part one, this is saying that we have some student that didn't visit at least one room in all the buildings. Okay? So imagine like every possible building in AUB, there's at least one room in each of those buildings that you didn't visit. So part one, we have to say that. So there exists a student S1 such that there exists a building for all the rooms in that building. He didn't visit any one of them. Okay, so just up to here. Do you understand everything up to here before going to the right? So there exists a building for all the rooms in that building. So for all the rooms in this building, the student didn't visit any one of those rooms. This is equivalent to saying exactly one student didn't visit at least one room in all buildings or didn't visit any room in some building. So this is what we did. We said that this student didn't visit any room in some building. Okay. Now the second part, we have to say that every other student actually did visit all the rooms. So for every student, for every building, there is a room such that if this student wasn't the first student, then S2 has visited this room. Okay. Now they're saying, so the second part was just the opposite of what we wrote for that student. They're saying review what would happen if we removed the first part. So what would happen if we removed the first part? Would the translation still be correct for F? Like, in other words, do we need part one or is part two enough to solve F? Well, my answer is no, we shouldn't remove it. It's important. If we did remove it, all we're saying is forget about S1. Every other student than S1 has visited some room. But since we didn't say anything about S1, then S1 could have also visited those rooms. So you're no longer saying there's exactly one student that didn't do that because you didn't tell me anything about that student. So I want you to try and imagine this with me. Whoops. Okay, I can't. If I change the color, all the colors are gonna change. Okay, sure. Let's just go with blue. I wanted a different color. Let's say here S2 is S1. Is this confusing? It shouldn't, because we're saying for every S2. S2 is just a variable, right? We're saying for every S2. So S2, it could be simply all the students. This is like saying for every X. So if I want to be technical, S2 1, S2 2, S2 3, and so on. But focus on just the 1, 2, 3. So for every student, if this student is not student 1, then I know that he visited some room. If this student is not S1, blah, 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 I know he visited this room. Well, what if I reach one of the students and this was false? False where like the student is S1. So this statement is false. If it's false, what could I conclude about the implication? Nothing. Because we know that false implies false is true. And we know that false implies true is also true. So if this student, if this is false, like, hey, now we're working with S1, so this implication, the first part is false, we can't deduce anything about on the right. The NRB is at least one room. Well, we're saying for every building there exists R. So for every building, this room is in this building and the student visited R. So yeah, it's at least one room since we said there exists R under all this blue scratching. Okay. If you got confused what I was trying to draw here, don't worry about it. I was just saying it in different words. Like if this is S1, then S1 like if S2 is S1, then S1 being different than S2 is false. Because hey, it is S1. And if it's false, we can't deduce the right part. So we're not saying there's one student that didn't do that. Oof. That was a lot of words and a lot of time. Let's move on. Any questions before we go into 6? Okay. With the domain of swans, consider the following functions: s of xy, pxy, xy. Express the following and then their negation, both quantifiers and English. Okay, let's see part X, part A. For every xy, s of xy, if and only if, or equivalent to s of yx. This is actually symmetric relation. So it's like if you have a predicate that says xy, it's the same as saying p of yx. This is symmetric relation. Like you have symmetry. Like you can flip the variables. So if x is a sibling of y, then y is a sibling of x. So this works with the idea of siblings. Like if you have a brother, then this brother is your sibling, and you are his sibling. So symmetry works here. Let's see what they said. For any two swans, if one is a sibling of another, then the other is a sibling of the first. What's the negation? XOR. Why? Well, when does equivalency work? It works when if the left side is true, then the right side is true. Or if the left side is false, the right side is false. What's XOR? It's the exact opposite of this. XOR is this. Either true and the other guy is false, or false and the other guy is true. So yeah, XOR is kind of the opposite of equivalence. Sure. So we read it as there exists a pair of swans such that the first is a sibling of the second, but the second isn't the sibling of the first. It might not make sense, but this is the translation. Like your brother is your sibling, but you're not his sibling. Okay? For every x, y, z, transitive relation. If you have s of x, y, and then you have s of y, z, you can kind of like skip the y or join the y together and it disappears. You get s of x, z. This is similar to what? To hypothetical syllogism, whatever it was. So P implies Q, Q implies R. You can, if they're both premises, then you can kind of do this. You can conclude P implies R. So you could say that this is a transitive relation with implication in this case. Okay. So if a swan is a sibling of a second swan, and this second swan is a sibling of a third, then the first is a sibling of the second. What's the negation? Just put a knot and do it. So first, the quantifiers get the for every becomes there exists. So there exists x, y, z, such that this. So there exists a pair who aren't siblings but share a sibling. Sure. Any problem with this or the rest of the exercise? Okay. The second part of this exercise is just going backwards, I believe. You have the English statements, you want to go backwards. So let's just look at the first one. All swans share a common parent. All swans who share a common parent are siblings. So for every x, y, z. So z is a parent of x and z is a parent of y, then x and y are siblings. And you do the negation and you conclude. Okay. I'm going to move to exercise 7 just for time's sake. If you have problems with the rest of the parts, let me know. I definitely advise that you should go over the solution again even after this session. So while you're studying it on your own, if you find something you don't quite get, please use the forum. Okay. Exercise 7 and 8 are kind of the same thing. You want to use rules of inference to reach the conclusion, or check if you can reach the conclusion. But here we're using propositions. Here we're using quantifiers and predicates. So you actually have to translate them into propositions. Now in solution A, it wasn't translated. They just kind of did it directly. But while you were solving it, you actually had to translate it, kind of like in part B. So I am cheered up or I am upset. C is I am cheered up. U is I am upset. And you translate the rest of the sentences. Then, this is the important part. After translating the sentences, you get all these premises, and you want to see if you can reach the conclusion, which is like the last statement. Then I am upset. So using all this previous information, you want to check, hey, can I conclude then I am upset? Well, this is what we got. These premises. Can we conclude U? A quick look at it says, yeah. Like, if you have, like, the first statement is saying C or U. So either C or U is gonna be true. Either C or U, maybe both are gonna be true. The way I see this, we're probably gonna prove that not U is true. So using simplification, or not simplification, disjunctive syllogism, we can get rid of U and we, never mind what I said. Or actually, we're probably gonna find not C and remove the C, and then we can conclude the U using disjunctive syllogism. Okay, let's just go over it. C implies M and J. Contrapositive. This might be interesting. You may have not done this in your solution, but we know that contrapositive has the same truth value as implication. So C implies M and J is a premise. So it's true. But the contrapositive is also going to be true. M and J implies not C. It's also true. So we wrote it here. De Morgan, enter the not. Premise, not J or M. De Morgan's of 4, simplification of 4, and then a very smart idea of adding or not J. Why? We know that not M is true. Not M or anything is also going to be true. But we add not J because of 3. So now with 3 and 7, we can do modus ponens and get that not C is true. C or U, so C is false, disjunctive syllogism. We get U. Good. Inference rules are like the really core exercises. They might look difficult, but when you practice a few of them, you feel like the ideas just flow. This might be one of the slightly more difficult questions because we're telling you, can you reach the conclusion or not? So in part B, we were able to, but in part A, they say you can't. So here, the hard part is you're not sure, can I reach the conclusion or not? I kind of felt that we could because we have C or U. And yeah, it was just a hunch, and the hunch was right. It could have been wrong. Okay? Do you have a problem with C? Look at it on your own after this session, and let me know if you have any problems. Please, let's try to use the forums for this stuff. It'll be nice to have a discussion between us if somebody doesn't get an idea. Again, exercise 8 is the same, but now we're going to be using predicates and quantifiers. Again, I'm going to do just the first one because we're almost out of time. All healthy food tastes good. some food are not healthy, then some food doesn't taste good. They're saying it's not valid, like we can't reach the solution. Let's see why. H of x, x is healthy. T of x, x tastes good. We have, for every x, h of x implies t of x, and there exists x, not h of x. Makes sense, right? For every x, if this x is healthy, then it's tasty, and there's something that's not healthy, can we conclude that there's something that doesn't taste good? I'll say it one more time because even I'm not completely focused at the moment. For all your food, if it's healthy, then it's tasty. This is your first premise. Your second premise tells you there's a food that's not healthy. There exists some food that's not healthy. Can you conclude that there exists some food that's not tasty? We already know that it's not, but let's see why. I hope you kind of are getting a hunch of why. Like if I tell you all tasty food, all healthy food is tasty, and there's something that's not tasty, that's not healthy. Can you conclude that there's something that's not tasty? No, why not? Maybe that unhealthy food is probably tastier than the healthy stuff. So part one, for every x, h of x, t of x, universal, what's the word? Instantiation. H of a implies t of a. Because for all food, this is correct. There exists x, not h of x. ei, we get not h of a. And this is where you get that, it's not valid. Because you have 2 and 4. And just like I was saying above, maybe here it'll be more clear what I was trying to say above, way above. We have h of a implies t of a. It's true. We also have not h of a is true. If not h of a is true, that means h of a is false. If this is false, t of a can either be true or false, and the whole statement is still going to be true. This is why we can't conclude not x. This is why we can't conclude this guy. Because the conclusion says there's some food that's not tasty. But as you can see here, we can either conclude t of a, or we can conclude not t of a. Like both of them would make the implication true. So this is why it's not valid, and the action. So concluding not t of a is a falsy of affirming the consequent, and therefore the argument is not valid. So if you say, hey, not tasty, you're affirming the consequent, which you can't do. It could either be true or false. This is what I was trying to say about the student thing. Did I miss it? Way up here. This is what I was trying to say. Once S2, since S2 we're passing over all the students. If S2 is kind of like annoying, just think of it as x, like here for every x. For every x, if x is not S1, implication then he's in some room. But if x is S1, so this first part is false, you can't conclude anything about the implication. So you can't conclude that, hey, not he visited a room, so you're done with except one student. You can't, the right part, you can't deduce. It could either be true, it could either be false. So this first part, you can't remove it. It's necessary that you specify there's some student that didn't visit. So actually the first part is saying there's a student, and the second part is saying he or she are the only students. So exactly one. I hope this made it more clear if it wasn't before. Okay, it's 6 o'clock, but let me finish the last exercise. If you have problem with, okay, so we did part A. If you have a problem with these parts, let us know in the forum. Exercise 9, and I'm not going to waste a lot of time on exercise 9 because just like I guess exercise 2, we kind of went through over this in the recitation. So part A, for every x p of x, or there exists q of x, is this equivalent to this? Yes, it is, because this x is different than this x. So you could say y. There exists y of q of y. Trying to understand it, it's simply two x's. The x's are different, so hey, just say that the other one is y and put it at the start. But the actual proof, well, there's 3 different solutions for this. The second solution is what we did in the recitation, using universal instantiation, existential, then the generalization. It's not hard to follow, so you can see it on your own. The first proof is nice because it's kind of using the normal proofs we've been accustomed to, so far. So, for every x or there exists x, simply you can switch the x by y because, hey, it's just a variable name. You could have said there exists your name, whatever it was, as long as you use your name as a variable and not as a constant. For every x p of x is this. So for every x p of x, you want them all to be true. That's why we have ands. Or there's some y that makes q true, which is why we have the ors on this part. Distribution. All of this or this. All of this or this. You keep going, all of this or this. This is like a general distribution. If you don't see it on a scratch paper, just do it for 3 variables. Like do it for x1 and x2. And the third one, or q of x1, and then or for 2 and 3, and distribute them. You have all these 3, or this one. Then you have all these 3, or the second one, or the third one. This is what they did here, but it was in general. And then at the end, you can do, you reach the right side. Or ask me right now. There's a third way that I'm not going to read. So you let me know what it means. Part B. It's easier. And they use the same solution that we did in the recitation. So we're saying for every x, p of x is equivalent to for every x, q of x. Is this equivalent to saying for every x, p of x is equivalent to q of x? So we're saying for all x, if they have the property p of x, then for all x, they also have, it's equivalent to saying for all x, they have the property of q of x. If we say that x is odd and q is even, this will be false, equivalent to false. Because not all x's, here x is definitely integers, not all x's are odd. So for every x, p of x gets false. Same thing, not all x's are going to be even. So for every x, q of x, it's going to be false. False implies false. So the left side is going to be true. It's true because false is equivalent to false. What about the right side? For every x, if x is odd, x is also, and then x is also even. And this is gonna be for, let's say if x is even, so it'll be here false and it'll be here true. If x is odd, it'll be here true, it'll be here false. So you can see for any combination, they're never equivalent. So the whole thing is one big false. We were able to find a counterexample such that the left side is one big true and the right side is one big false. So no, they're not equivalent. And that's that. Okay, I think I went over everything I wanted to go over. If you have questions that you want answers to right now, ask me right now. Otherwise, please go over the questions again and the solution. Like if you can today or tomorrow while it's still fresh in your mind. And you can use the forum if you have any questions. Okay, so any questions? You're welcome. Okay, so if you don't have any questions, you're free to leave. I'm gonna end the meeting in a few minutes. In a few minutes, if nobody asks anything. You're all very welcome. And Ahsan, I think while you weren't here, we just went over exercise 1 and 2, just like part B and part B. So if you had any problem with them, let me know. Okay. طيب, I'm gonna end the meeting. Thank you guys. See you next time. See you Thursday. Bye bye.